Yes, good morning, my calculus friends. It is time for another installment of glory. Let's see, I haven't busted in there, but I assume you all have a project for me that was, I don't want to say easy, but easier than some of the other insanity I have created. So I will go investigate that after class today. And so we have something lovely to talk about today. So I will share screen and we will get after it. Are you awake? Do you have anything that you need to ask me about? Burning questions on your mind about philosophy, my favorite subject? Like, I don't know. Just woke up, man. Leave me alone. Okay, the good news, my friends, is we have a few tools for integration now. Really, we've got substitution. We've got integration by parts, which I will abbreviate. And the good news, that's it. There is no more tools. That's awesome. However, the complexity of choosing the right substitution or even choosing which one of those two techniques to use is, as I've been beginning to hint at, really daunting. And so today we're going to tackle in 8.3 trig integrals. Trig integrals. And as I mentioned, this is what mathematicians do. They just decide integration's cool, and so then they think, well, let's integrate everything under the sun. And for your easy reading sometime, I would like to propose a book to you that I'm going to obey today called The Mathematician's Lament. It's by a nerd named Paul Lockhart. L-O-C-K. It's probably got a K in it. I don't know how to spell his name. I'll spell my own name. There's a K. That's a K. Just take my word for it. His overall point is we have utterly ruined mathematics as educators, and I kind of agree with him in the sense that all we do is just march people through kind of a rote process. You know, it's all segmented into chapters and organized neatly, and you know, you just kind of march through it and so forth, and in a rote fashion, and everybody follows the same thing. I mean, it's like Hitler invented math or something. And I kind of agree with him in the sense that you know, Matt and I, you know, what do you do? I mean, his idea would sort of never work, but his main idea is like people enjoy playing and trying to figure things out in life, and his proposal is like you should just play with math. I mean, you know, the type of person that's interested in that, obviously that kind of play is interest to everybody, but the idea of just playing around with things and trying to figure things out, and you know, having time and asking and answering interesting questions and so forth, and he's got a real point. And his I mean, I sort of can't change the entire world, nor do I necessarily know that I want to, but I do try to infuse some of his ideology because it's kind of got into my mind. And instead of just, you know, marching you through and showing you examples every day, I do try to kind of play around a little bit and give you time to think and, you know, try different techniques and so forth. And we're really going to do that today. So it's a really short book. It's like less than 1/4 of an inch thick. You can probably read the whole thing in an hour. It's really short. But let me remind you of something you already knew once before. Once upon a time, you knew the integral of the tangent. I showed you this once before. With respect, and I also want to open your mind a little bit. With respect to substitution, for instance, if I was to come up with an idea, I might say, well, let's let u be equal to the tangent of x. I mean, if I'm going to try substitution, because I'm just sitting there staring at tangent and I'm like, I don't even know what to do. Like we've sort of figured out the integral of cosine is sine and the integral of sine is cosine and so forth. And so we kind of got those two trig functions. When it comes to something like tangent, it's like, I don't even know what to do. I mean, there's nothing to do. There's only one expression there and I don't know what to do. So if I tried u equal to tangent, since that's the only thing I can think of, the other option would be integration by parts, given that I kind of opened up your mind the other day with logarithm to say, well, there's kind of a 1 there. In other words, it's 1 times the tangent of x. So maybe I could use integration by
tangent is sine over cosine, right? So can't we do integration by parts with that?
Yeah, and tangent, remember the identities, tangent can be switched to sine over cosine. Very good, Vale. And cosine, 1 over cosine could be considered to be secant. So in a sense, I could rewrite tangent as secant times sine, which means then I could attempt integration by parts. That's a brilliant idea. I'm glad you said that, Vale. Good observation. So maybe I'll even go this route. So that might be a substitution effort. And then let's follow up on Vale's idea with a couple of things. Like I could say integral of 1 times the tangent of x dx and try integration by parts with that. By the way, you definitely would have to call this one u and this one v prime if you did that. Because if you called tangent v prime, then you'd have to take the integral of tangent, which is the whole problem we have in the first place. So that's interesting thought. And then Vale's brilliant idea, which we will add here now, which would be to rewrite, since tangent is sine over cosine, and 1 over cosine is secant, maybe that with integration by parts. Now, again, what Lockhart would say about this is kind of fun. Like to sit there and just say, you know, we have a mystery on our hands here. You know, how are we going to figure out what the integral of tangent is? Or maybe if there even is one. I mean, that's the thing that's really cool. Like who says there's an answer to every one of these problems? Maybe there isn't an answer. Like for instance, pi, you know, what fraction is pi equal to? The answer is there isn't one. You know, I mean, maybe there's not an integral for tangent. And so, but is there a part of you that says that's kind of fun? That's kind of cool. I'd like to, I don't know, be released. And there's a part of me that says, let's burn the entire period, trying every single one of those and see where it goes. And I do that some in this class. I try to strike a balance because I know that, you know, lots of you just want to get this class over with and you got to be prepared for your assignment. And so I try to strike a balance there and sort of live in the world that I'm given. But I'm greatly influenced by his thinking in this regard. This is kind of fun. Now, having said all that, I don't really know what to do. Let's try the first one. Let's try tangent. Let's just see what happens with that one. Let's try u substitution. I can't help but play some. So let's try that one. Okay, if u equals the tangent of x, and this is a really important idea. I'm going to draw a picture of that. You should, if you can't do this, and I'm teaching this exact topic in trig tonight, Math 112, 5:30. Send me a let's see. No, I've been teaching this recently. Anyway, it doesn't matter. Can you draw a picture of that? If somebody mocked you as a nerdy mathematician and said u equals tangent of x, like what does that even mean? I rhetorically ask you, could you draw a picture of that? Could you say it looks complicated, but it's really not? Do you know what u and x are, like in the real world? They're not. I'm not talking letters. I'm talking, if you take the tangent of it. Do you understand that if you take the tangent of it, it's an angle? Like x has to be an angle. And since tangent is opposite over adjacent, then u is a couple of sides in a right triangle. And notice every fraction, every whole number is a fraction. You can put a 1 over it. So could you say to your questioning friend, dude, that's not that complicated. That's angle x right there, and tangent is opposite over adjacent. So it's just telling you the relationship between a couple of sides in a triangle. Now they're still not going to be satisfied by that because that's weird, but fine. Okay, anyway. So if I'm going to substitute, of course, I need rid of the tangent and the dx. And so let's go get a dx. So the derivative of u equals the derivative of tangent, if you remember, and you should have my sheet up from last term, but the derivative of tangent is secant squared of x. That's terrifying. I don't want to end up with such an ugly thing. And so I think I have all the ingredients I need. So I guess my new integral that I'm going to attack is now, well, u is the tangent of x, so I replace that. And then dx is replaced by du over secant squared of x. And so that's kind of disappointing because that didn't get rid of all the x's. How can I get rid of some brilliant person in this class? How am I going to get rid of secant of x? Like it's still an x. Channel your math 112 nerdness from earlier in your life when you used to be good at this. Here's a hint. Look over there at that triangle. That triangle gives you a way of replacing the secant of x. Do you see that? This is a skill we're going to need in this section anyway, so this works out good.
Wouldn't it be 1 over u?
Close. That would be cotangent. Which two sides does secant divide?
The hypotenuse over adjacent.
Yeah, so I have this memorized. I don't know what secant is. I know what cosine is. Cosine is adjacent over hypotenuse. And then I know that secant is that upside down. Like that's kind of my stupid way of memorizing it. Well, because of Pythagorean theorem, you do know that this side is u squared plus 1 squared. And since secant is not adjacent over hypotenuse, but hypotenuse over adjacent, then I could say the secant of x is equal to, fortunately it's over 1, so that's just that. And then look, I get to square it. Would you agree, mission accomplished? We have succeeded in converting this to something else.
Yeah, and it looks a lot simpler to integrate.
Yeah, and at least I made it into something that looks familiar, right? Because before it was like tangent, and I don't really know what the heck that was. Does that look doable to you? Is this any better? Did we get it? I mean, it looks better to me. I agree with Justin in the sense that it's like, I feel like, oh, okay, at least it's not got the stupid tangent anymore, which I don't know what to do with. Can you do this? Is this easy? Is this, I don't know.
Yeah, we'll just do a second level of u substitution, right?
Yeah, I was going to say for the denominator.
Yeah, notice the derivative of what's on the bottom. Remember, we don't like plus signs on the bottom. The derivative of that is sitting on the top. This is really good, actually. And I didn't expect this, honestly. Actually, I was going to show you something totally different. And true to the nerd Paul Lockhart's concept, I think this is actually going to work, which I didn't expect, honestly. So, again, if we let's let W, whoa. Let's choose another letter. Let W equal u squared plus 1, so that I don't have a plus sign on the bottom. And that would mean that dw equals 2u du. So what's my new integral? Well, I've got a U on the top. I now have a W on the bottom. That's a very exciting. And then the DU gets replaced with DW over 2U. Bam. Those cancel out. And so now I really can do this. Do you agree with that?
Yes,
So
Doug.
if I poll, go ahead.
I was just agreeing with you because it was quiet.
Yeah, I was also going to say that I remember at the beginning of this, I think I remember you saying when we were looking at the calculus notes how to notice that like tangent didn't go the other way, and that was because it was something we would learn later on down the road.
Yeah, remember, if you look at your calculus notes, there is nothing of which you take the derivative and get tangent. Therefore, we don't know what the integral of tangent is. But it looks like we're about to figure it out. What's the integral of 1 over junk?
The
Natural log of junk.
Natural log of junk. So this would be 1/2 natural log of W. Bam. Except for this problem had no W, right? What was W? U squared plus 1. So that'd be 1/2 natural log of U squared plus 1.
Then would you just substitute back in again after that?
Yeah, but there was also no U. So what was U? I don't know. I forgot. What was U? There we go.
Tangent x, right?
Tangent of x. So it's finally, I guess, 1/2 times the natural log of the tangent of x squared plus 1. Wow. That's the integral. Now, do you have the cheat sheet? I posted it on my open math for you. Anybody have it up? That little cheat sheet of integrals. Does anybody have that where they can find it? I don't, so that's why I'm asking you. Or get your, I could actually just ask my iPad right now and do the same thing, but that's not the answer to the integral of natural log. Like according to a table, the integral of, I'm sorry, I said integral of natural log. The integral of tangent is what according to a table? Does anybody have that up?
It looks like negative ln cosine of x.
Cosine of x?
Yeah.
Negative natural log of the cosine of x. So if that's true, I like that better, don't you? Except for that's not what we got. Because that's nice.
I was confused on the triangle part because U equals tangent x, but isn't tangent x U divided by L, and then we substituted that for, I was kind of, maybe I'm just bad at pre-calc. I don't know.
No, feel free to ask. This is 1, not L,
Oh, okay.
because we said that U equals tangent of x. Tangent of x is opposite over adjacent in a triangle. And so I had to make U into a fraction. So I said, oh, well, any number can be a fraction, just put it over 1. So tangent of x is U over 1. So that means angle x, tangent is U over 1. Okay, cool. And then because it's a right triangle, then I can square these, add them together and square it to get the hypotenuse.
Gotcha.
Who knows their trig identities? I have this vague recollection that there is an identity that had tangent squared in it. When I say vague recollection, despite the fact that I've taught that like 100 times, I don't know what it is.
Tangent squared equals secant squared minus 1.
Yeah, so let's tangent squared equals secant squared minus 1,
Yes.
or tangent squared plus 1 equals secant squared. Is that true?
Yeah, yeah, that's actually what's written on my paper. I just did it the other way because I felt like we were gonna have to know what tangent was.
I'll erase this, but watch this really quick. Can you make this kind of stuff for yourself super quick? Like the one I have memorized is sine squared plus cosine squared equals 1. Notice I'm not speaking to you. I'm just speaking to my own mind. And I need something with tangent in it. Well, does it make sense if I divided by cosine squared? Sine squared over cosine squared would be tangent squared. And then I'd have to divide all of these by cosine squared. And 1 divided by cosine squared is secant squared. Okay, yeah, tangent squared plus 1 equals secant squared. I reminded myself. Does that make sense? So, look it up if you can. You got your phone, whatever. But this is the same thing then as 1/2 natural log of the secant squared. Well, that seems like progress.
See, I remember learning about those identities, but I don't remember being shown that, and that is extremely helpful to realize, the tangent and cotangent parts of it. That's interesting.
Yeah, make it for yourself. And when you're learning something the first time, like for instance, what I just showed you up there, probably not all of you are tracked with that. I mean, I'm rambling along. It's like, hold on, like slow down, push pause, like let me think about this for a second, because it is drawing on a bunch of trig knowledge that you at one time had, but probably, as you just said, Justin, probably didn't understand deeply enough that you could make it for yourself. How about your natural log knowledge? What's cool about that 1/2 right there? Where can that 1/2 go? Who remembers this? That 1/2 can fly up here. Remember that? And then isn't that saying secant squared square root? Isn't that the square root of something squared? Which means the square and the 1/2 go away. So now we have the natural log of secant. We're getting darn close to this answer now. Do you notice that? So you could stop there and say the natural log of secant, or you could say the natural log of 1 over cosine, because if you're like me, you don't like secant, and it's not a button on your calculator.
Can't we just make it negative and flip it? And then you have your answer?
Exactly right. And isn't that the same as the cosine of x to the -1 power? And can't that -1 fly back out in front? Hey, that's where they got that answer. I do like that answer better, like the one they put in the table.
Yeah, it's more simplified.
Yeah. I don't really like the exponents. I don't want a -1 there. I don't want secant there. So let's throw the negative out front. So we did it. Amazing. And again, I honestly didn't think that was going to work. Like I didn't even know that was going to happen. I figured we were going to hit a total dead end and it wouldn't go anywhere. For extra credit, or maybe just because you have not lost all of your sense of creativity, go run down those 2 rabbit trails and see if they go anywhere. Maybe all 3 of these work. Again, I am so tempted to burn the entire class just playing with that stuff because I really do think that's kind of fun. I think mountain biking is more fun, but this is fun. There's play of the mind and there's play of the body. They're all awesome.
Yeah, I'm feeling the play of the body today from this weekend.
You need to rest more, Justin. You're getting along in years.
They built those really big jumps right next to Comer, and that was the lift I was working on. So it was, that was what I was doing.
Yes. Jumps are my downfall too. No pun intended. Let me show you a much easier substitution for tangent that relates to Vale's idea earlier. So in a sense, again, can you see what I've said before? The concept of having a trig table, like let's never do that again. It's kind of fun if a year goes by just to say, you know, can I make this for myself again? Just like I did with sine squared and cosine squared in 1, I remade tangent squared plus 1. That's kind of cool to do, but for the most part, like that was a 2-step substitution problem. And so, you know, let's not do that again. I mean, that was pretty challenging. Let me show you a much easier substitution. Much easier. The integral of tangent of x dx, couldn't you just switch that into, as Vale said, sine over cosine? But who sees a really cool substitution you could actually just make right there? And I would doubt you do. Like, this is not obvious. This is what I showed you before, I don't know, some weeks ago, maybe. Watch what happens if you let u be equal to the cosine of x. Now, the reason this is a good idea is, just like a minute ago, didn't we notice that this statement right here, the fact that the derivative of u squared was sitting on top, we actually knew, or you're beginning to understand substitution. That's the best case scenario for substitution. Its derivative is sitting on top. Well, see, I noticed the same exact thing down here. The derivative of cosine is sitting on top. Watch how quickly this mess goes away when I make that substitution. So that means du would be equal to, well, the derivative of cosine is the sine, and the derivative of x is the derivative of x. So does this not, my friends, become the integral of the sine of x over, well, I let u be cosine, so that's u. And then dx, if I solve this equation over here for dx, isn't it du over negative sine of x? Do you see how nifty that is? That's, again, the classic substitution case. Oh, wow, that is rad. That means I don't have to like go to the right triangle to, you know, figure out what to replace it with. Bam, it's gone. So I just get, I guess, -1 if I pull that negative outside of 1 over u du. And isn't that just -1, the natural log of u? And isn't u cosine of x? And so we just have negative natural log of the cosine of x. Bam, 1 substitution, 3 lines, boom, I'm there. Is that kind of cool that you can get it more than one way? Again, I love this illustration for math because it's like driving. There's like 50 ways to get where you're going driving. Is there one that's the fastest? But unless you're really good, or unless you've lived in the town a long time, or unless you have Siri telling you what to do, you're not going to know the fastest way. But Paul Lockhart's point is, who cares? Like, who wants the fastest way? Play around a little bit, have some fun. The fact that you can do this 2 different ways, I think, is amazingly cool. And we're wondering if you couldn't even do this 4 different ways, or maybe there's even another idea that we didn't think of. That's kind of fun.
Yeah, I think that was like my favorite part of trig, was learning those things.
Yeah.
And realizing like what they actually meant, because like everything before that was just like, oh yeah, x and y, and this is how they work together, you know, which was like, okay, that's cool, but I don't really understand what that means.
Yeah, trig's a weird one because you can always switch it out. Like, if you, no matter what trig expression you have, you can always make it into something else and then try your hand at that. And so now, my friends, now that we've solved tangent, and I feel inclined to fill this last little space here with the truth of what we have discovered. Notice I'm being a little lazy here, and I'm not putting dx, and I'm not putting plus c at the end of that and so forth like I should. But, you know, we discovered that. And so now let's jump to something much more terrifying. The integral of, well, let's try the other ones. Like, what do we have left? We got cotangent By the way, cotangent would be cosine over sine. Does it make sense you could use the same technique we just did with cotangent? My guess is, and I actually don't remember this, but my guess is the integral of cotangent is probably like natural log of sine or something like that, just because it's so similar. But I bet that's it. And I don't know if it's negative or positive, but I bet it's that. But what about secant and cosecant? Oh boy, wonder what that would be. Again, is there an answer to this? If there is it complicated? We just saw that remarkably somehow the integral of tangent got logarithm involved, which just seems insane.
Secant is 1 over cosine.
Yeah, so let's kind of brainstorm here for just a second. Let's kind of brainstorm kind of what we might try. So Justin said it's 1 over cosine. So, you know, that feels better because it's a cosine. But notice the sine's not sitting on top. So if you said, let's let u be cosine of x, that's not going to work out quite so nice. That doesn't mean it isn't going to work, but that's not necessarily going to be so nice. But let's just keep pouring ideas out. Like what else could we do? We can start with that. That is a substitution, by the way. We didn't change letters, but isn't that a substitution? Secant of x is 1 over cosine. We just substituted. We didn't change letters, but that's a substitution. So maybe that's worth trying. What else? What other options could we try?
Is it an option just to let u be secant of x?
Exactly. It's always an option.
Could we also do integration by parts if we said 1 times secant x?
Exactly. If we say 1 times the secant of x and do integration by parts. And again, if we're going to do integration by parts, do you agree that u has to be secant? Because if you made v prime secant, then you'd have to take the integral of secant, which is the problem we're trying to solve. So that's not going to help us. Let's see. I'm out of ideas. Well, I'll throw one other one out there that probably wouldn't occur to you. A second ago, didn't we just remind ourselves that secant squared is 1 plus tangent squared, right? So if that's true, couldn't I substitute secant squared is 1 plus tangent squared? So isn't that what secant is equal to? Again, isn't that a substitution? But I just didn't switch letters. Now that
But
looks
isn't
like,
that,
go ahead.
sorry,
No, go ahead.
but isn't that secant squared, not secant?
Yes, but I square rooted both sides. In other words, I had secant squared equals tangent squared plus 1. And so then I square rooted both sides.
Oh, okay.
Thank you for immediately interrupting, Eve. I want all of you to do that. Otherwise, the conversation is lost. Interrupt immediately. So, you know, part of me looks at that tangent squared and says, hey, we now know the integral of tangent. But then I think, oh, geez, there's like a square root there. And so, you know, if I did do that, then I guess my first move would be to let u be equal tangent squared plus 1. I mean, again, do you find yourself going, that's really cool that we brainstormed 4 ideas there. I wonder if any of them will get us there. I do not know the answer to that question. I do not know if any of those will get us there.
Can we go down Justin's rabbit hole? Because I think that would be the first thing that would jump to my head on a quiz or something.
Number 1?
Yeah, number 1.
Yeah, I actually do want to pick one of these and just kind of see where it goes, just for the fun of it. So you proposed it, let's do it. And so therefore we will say extra credit for these. And by the way, extra credit doesn't mean you're successful. To me, it counts if you're able to switch it into a new world, even if you can't solve what's in that new world. So I'm not looking for success here. I'm just looking for you to play around with it a little bit. But let's try Justin's idea. So if we did do that, you correct me if I'm wrong, but I don't really see any choice but to let u be cosine of x or something like that. Is that what you guys think? Anybody have any other ideas that they think are promising? I'm sort of not afraid of that because I understand the answer to cosine. In the sense we have sine, cosine, and tangent now. So if we see those, we're not afraid of them because we know what those are. I suppose I could think of cosine of x as to the -1 power and then think integration by parts. I suppose I could try that too. But let's try this. I don't know. And again, I'm not kidding. I don't know. So let's see, that would be du equals the derivative of cosine is negative sine, the derivative of x is the derivative of x. And so I think I have everything I need. So I have, instead of 1 over cosine, I have 1 over u now. But then I've still got that dx, which I realize is equal to du over negative sine of x. And remember, as I said before, that's a bummer because there's no sine of x on top to cancel. So tangent was easier. So now I'm still stuck with the sine of x. Does anybody know how we can get rid of that? You should all know now. Draw a picture of that. What does u equal the cosine of x look like? Cosine of x means x is an angle, u is sides on a triangle. So I'll make a fraction out of it. So this is a huge part of what you need to understand to tackle crazy integrals. So this is angle x, cosine is adjacent over hypotenuse. So I know two sides. So now can I get the sine of that angle without ever knowing what the angle is? Yeah, sine is opposite over hypotenuse. Well, I don't know the opposite. Well, you can find it using Pythagorean theorem. So the hypotenuse squared minus u squared square rooted. Isn't that length over there? So now I know what the sine of x is. So this becomes 1 over u times du over negative, and sine of x is opposite over hypotenuse. So fortunately, that's over 1. So I guess I could, take the -1 out in front. And so what I really have then is just 1 over u times the square root of 1 minus u squared du. Again, success. I got it into a new world. I got secant into a world that I understand.
That is super close to inverse secant, but not quite.
Nice. Yeah, it's real close to some things. Yeah, do you guys remember those? Let me see, can I pull that up? I can't remember if I made a copy of that in my... Someone's telling me I put this in here because I planned ahead. Bam. I did plan ahead. Does everybody understand what Connor just said? That's not what I wanted to do, apparently. Import. Remember how some things look like inverse? Which one did you say it looked like, Connor?
Inverse secant.
Yeah. Do you notice that it is so close to this? Isn't it that? Like, what's wrong? Why isn't it like that? What's wrong with that?
I think we have negative x squared.
Yeah, it's actually 1 minus x squared, not x squared minus 1. And unfortunately, you can't just take a negative out of that because remember when you square root stuff, it pops out squared. And so you can't actually get rid of that. That is dang close to inverse secant right there. Now, of course, that'd be weird if the integral of secant was inverse secant. But it's like, and I'm really impressed that you noticed that, Connor. But it isn't. Like, it's darn close, but it's not. And it's also close to this one. Do you agree with that? Isn't that what we had? Didn't we have 1 minus u squared? Square root of 1 minus u squared? Except for there's no x out front, right? Dang it. So these were backwards. So let's make a note of that. Darn close to 1 inverse secant and 2 inverse cosine. No cigar though, unfortunately. Let's draw a cigar. There's a cigar, smoke coming off of it. No. You couldn't do better than that, Cheyenne, could you? Cigar?
I'm pretty sure I could.
Oh, that hurts. So when I say success, that means we got it into a different form, but we're not done yet. And so I guess we'd have to try another substitution. And my first thought would be, I guess I would try letting, say, w equal 1 minus u squared and see if I could get, because we don't, anytime there's like a minus or plus sign on the bottom or there's a square root, we don't like that. Now, I will tell you, we're not going to do this because this turns out to be, I think, I'm not sure, but I think this turns out to be a rabbit hole that we never climb out of. I think this leads to, you can always do it, but it'll lead to another integral that we can't do, which will lead to another integral that we can't do. And again, I'm not sure that that's true. What I want to show you is, in the interest of time, because we do have to make some progress here, is a breathtakingly brilliant substitution that some nerd like Paul Lockhart came up with, and I have no idea how. So, as I said, I'm assuming that doesn't work. Now, many of you are, thinking, well, I'm not sure it does, and so I want to keep trying. Or, is there some way to maybe make that look like, is there some algebra I could do to that purple statement there to make it look just like inverse secant or arc cosine, inverse cosine? Maybe there's something I could do. Or you say, I don't think, that green choice there is a dead end. Maybe that'll get us out of the woods. I'm not sure. Actually, I think I do want to quickly try that. We can do this really fast, right? So let's do it really fast.
Didn't you do a substitution of w equals u root 1 minus u squared? And just turn the problem into a 1 over w?
Oh, in other words, throw the square root in it as well?
And the u, just have it be u times root
the
1 minus
entire
u
thing.
squared.
Like
Yeah.
w, yeah. And notice, you see the infinite, it's just like driving. In other words, I'm going to go someplace. And so it's like, okay, great. I know it's like south. And so I start heading south. But then unfortunately, you hit a fork in the road. And then depending on which fork you take, that fork has forks. And then the fork you didn't take has forks. And so there's like no end to how many things we could try here. So thank you for pointing that out, Bale. So now I don't even know what substitution to try. So we got 3 of them now. 3 of them.
Couldn't you also multiply the top and the bottom by square root 1 minus u squared?
Yeah. In other words, move it around a little bit. So like do some algebra to that purple equation. So if we multiplied the top and the bottom by the square root of 1 minus u squared, maybe algebraically that would look different, because it would end up looking like the square root of 1 minus u squared on top, and on the bottom, the square root would go away, and then you could distribute u in there so that it'd be u minus u cubed. So maybe there's where I should make my substitution. And so thank you guys for, I didn't think of any of those ideas. Man, it's like, is there some way out of this mess? Does one of those actually get us there? Do they all get us there? Do some get us there faster than others? I mean, isn't that kind of fun? That's why I introduced kind of Paul Lockhart's book. And if I was sort of rich and had infinite time, it's kind of, I want to run down every one of those rabbit trails and kind of see where it goes. And there's no guarantee. You could end up doing 10 substitutions, and maybe you just go in circles, or you never get out of the woods, or you get lost or make a mistake. But it could be after 10 substitutions, you actually get the answer to it. I mean, it must have been amazing for the first person to figure this out, because don't you feel like, man, this is daunting. I don't know what to do now. Let's at least try quickly the simple one that I proposed. And I only want to choose that just because it seems like it'll be fairly quick, and I just want to get it into a new world. So let's see if we can pull that off. So I take the derivative of w, I get the derivative of w. If I take the derivative of 1, I get 0. If I take the derivative of u squared, I get negative 2u times du. So I have all the ingredients I need now to transform that integral, at least I think I do. So I have a negative out front. I've got a 1 on top. I've got now the square root of w. I've still got a u out here. And then du is dw over 2u. So I still got some u's. The u's didn't cancel. I wish one of those would have been on top and one on the bottom. Does it make sense we would have got out of the woods if that was the case? Am I sunk?
Well, u equals u equals root negative w minus 1. From the right there.
Yeah, nice job, Bale. And even better, what's u squared equal to? Like, I don't need u, I need u squared. Is it u squared w minus 1? Again, success. Success in the sense that I got it into a new integral, but I couldn't do it. Again, success. I got it into a new integral, but I still can't do it. So again, what's your next thought? My next thought would probably be, and again, this is just one of the original 4 forks. Remember, we had 4 forks to start this problem that you guys proposed. We chose the top one. And then I made the only substitution I could think of, which was to let u equal cosine of x. Then we got to u, and then you guys proposed like 4 different substitutions I could try right there. And so we took one fork, and that had 4 forks, and we took one of those forks. And now I'm here. And so my next thought is, I don't know, could I let u be equal to, I don't know, square root of w? Or maybe u is equal to w minus 1, like
would it be negative w plus 1 for your u squared? Because
actually, I did this wrong in my, I did this wrong in my head. I got to fix that. Thank you. In other words, what I did in my head is I added u squared to this side, and then I subtracted w over. So it should be 1 minus w, not w minus 1. And can you appreciate if this ended up taking like 6 steps and you made some stupid mistake like that? That would be really brutal. Because how long would it take to find it? Like, oh my God, you'd never find it.
I'd really feel bad for the person who has to grade it.
I know, that's me, so don't do that. You see what I'm saying though? Like, we just made 3 substitutions on one of these options up here and they work. That's amazing. It's really cool. You made it into a totally new problem. Yet we still can't do it. And so, do I give up? Is this just going to be endless substituting and I never get anywhere? I honestly don't know. What I am going to switch to is to show you a substitution for this, as I said, that some nerd came up with, and I have no idea how. This is totally from left field. So Jeez. I quit. No, that's not a question mark. That's an exclamation point. Now, was that a waste of time? Absolutely not, because I'm trying to teach you how substitution works, and the ability to, carefully, slowly, algebraically make these switches is one of the key skills to really hard integrals. And again, we don't have time. We don't want to be really good at this. But this is what substitution really is as a skill. Let me show you a brilliant option for the integral. What we're doing again, I almost forgot. Integral of secant of x dx. So we haven't been near as successful. This was very painful. If I was the first one to even ask this question, I would start to wonder if it was even possible. Well, not yet, because we have 8 possibilities here we haven't tried, and I even quit. I quit instead of continuing with what might have been promising. I don't know. Prepare yourself for insanity. Let u be equal to the secant of x plus the tangent of x. I'm going to give you a second to try to make that substitution yourself. First of all, would you agree that makes no sense at all? Where did that come from? Why would you ever choose that?
Oh, because you're introducing the tangent because du is going to bring it back in and then it cancels out, right?
Perhaps it'll cancel something, but notice there's no limits to what you pick. Like you could let u be equal to the secant squared plus the cotangent cubed. Like you can let it be anything you want. And remember, trig has kind of a circular sense to it. Like, every one thing turns into something else. And so I just want to give you a second. See if you can proceed to the new problem you now have with that ridiculously brilliant choice. And you should be able to. Like you should be able to do this. I'm going to catch up to you. So if that is true, then I'm going to need to get rid of dx as usual. So I'm also going to need dx. So I'll take the derivative of both sides. The derivative of secant of junk. Don't you have to look that up? Did you have to look that up? I don't remember what that is. Actually, I do now because I looked it up the other day. But the derivative of secant is secant tangent. And the derivative of tangent, we love plus signs, is secant squared. And the derivative of x is the derivative of x. Now, when you see that, you should say, yep, this is a dead end. That was a dumb idea. I quit. Let's go do something else. That just seems like a really stupid thing to do. Bad choice. But we have what we need. So let's write it out. The original problem was the secant of x. And we now, if we solve for dx, we have to divide by all that junk. Then we get down here, secant of x, tangent of x, plus the secant squared of x du. Do you agree with that? So this is clearly not going to work because it makes a disaster. Like, look at all the x's. There's x's everywhere. This is dumb. Should be your instinct. And yet, Don't give up too quickly. Notice on the bottom, both of those terms have a secant in them. If I factor that secant out, it leaves tangent of x plus the secant of x. True? Oops, that's du. Do you see now that this is actually going to come out of the woods and what looked like a trail heading in completely the wrong direction? First of all, those two secants go away. Sweet, some x's are gone. But now what do you notice?
Isn't tangent of x plus secant of x an identity?
No.
You forgot
Squared,
the
baby.
square on secant x.
Look at our original statement. Tangent of x plus secant of x can be replaced with u.
Gross.
So it's 1 over.
So this is just 1 over u du. The integral of 1 over u, natural log of u.
Whoa.
There was no u. There's no such thing as u. Replace it with what it is. Secant of x plus the tangent of x. Done. Wow. That takes my breath away. Who came up with that? What year did they come up with it? Was it utterly luck? Like, did they just spend months like thinking, not giving up? There must be a way. All math is beautiful. There must be an answer to the integral of secant. I mean, I wish that wasn't lost somehow. I wish there was a journal by the person that thought this up. And I wonder if they reasoned their way to this or if it was utterly luck. Do you understand what I mean by that? Oftentimes it turns out that it isn't luck. In other words, they don't just kind of, I'll try this. But I wonder if they tried 500 things. I wonder if they tried 5,000 things. I wonder if they tried 4. I wonder if one of the ways we suggested earlier actually worked. And then that led them to reason, hey, this is cool. This is faster. This is a neat shortcut. I wonder if they figured it out somehow.
So you can just add whatever you want to your substitution to try to work with it. Is that basically what happened when you said let u equal secant of x plus tangent of x?
Yeah, the point is you could pick anything you want. In other words, you could say, I think I'll let u be equal to the sine of x plus x cubed. I mean, you can try anything. It's just, it seems dumb if it's not related to the original problem. Does that make sense? I mean, you could try u equals the natural log of the sine of x. That's what I'm going to try. Anything. It's just that we tend to pick things that we see sitting there. Does that make sense? Like we did. A second ago, we switched it to 1 over cosine and we said, well, let's let u equal cosine because it's sitting there. But could we say u equals sine and maybe that comes out awesome? Or when we were sitting here with 1 over.
Because the thing is when we were first asked possibilities of what could be done, like besides seeing the 1 over cosine, I also saw that the derivative of secant was secant times tangent, but I was like, well, I don't know if that really helps, but I did see that, and that.
Yeah. My guess is they probably, whoever figured it out, probably tried lots of different things and they began to realize like, hey, I need stuff to cancel out. I want to avoid, where did I see that? I mean, when I end up with a bunch of u's everywhere, it's like I want them all to cancel out somehow. And so maybe that person, whoever that was, worked really hard to kind of make it work in such a way that things canceled out. Real mathematicians are usually really creative, really brilliant folks. So I imagine they practiced this enough that they started seeing some patterns to it. I doubt very much that was an utterly blind guess. But again, what am I showing you? I'm showing you what someone showed me. I didn't invent this. I never would have thought of that. I'm not patient enough. I would go mountain bike riding before I made it to my 50th attempt at this or whatever. But I think that's incredibly cool. I mean, I'd love to have been there when the person like figured it out. Oh my gosh, I'm the first human on the planet that knows the integral of secant. Like that must have been awesome. I don't know. That's just, I find that crazy. Unbelievable.
Yeah, if there was a journal of their attempts, it'd probably be like day 50. I have tried this substitution and I have gone down this path so many times. Is there an end in sight?
Yeah. And I wonder at some point if they started to wonder if they shouldn't switch their intention. By the way, this is what mathematicians do. If they tried 50 times, you can't actually switch your attention to try to come up with some way to prove it's impossible. That would be cool if you could sort of prove it's impossible, because then at least you could quit. Which of course, doesn't that feel daunting? How would you ever prove it's impossible? But mathematicians are remarkably brilliant at coming up with that. The proof that pi is not equal to a fraction came up as a result of that. It was a proof that somebody came up with after trying everything and not finding it. They came up with a brilliant way, a really neat way to prove that it was impossible to do so. You probably heard of WD-40. You know why it's called WD-40? WD is water displacement, it's the stuff you spray on things to make it lubricated. 40 was because it was the 40th try. You tried all these different mixes and so forth. So WD-40, water displacement 40. 40th try, got it. Now he's a millionaire, billionaire, whatever.
I actually did know that.
You knew that?
I did, yes.
Yeah. Some of you are like, I don't even know what that product is.
It's terrible for bearings, actually.
True, it's very corrosive.
It's good for a minute.
So do you realize this opens a terrible Pandora of questions now? Like and notice we didn't do cosecant, but you've got a sheet now. Like you've got the answer to cotangent and cosecant. We could create them in a similar way. Again, if you're a curious person, try to invent the integral of cosecant yourself. It's probably some similar substitution. It's probably let u equal cosecant plus cotangent or something like that would be my guess. And so we know the integral of the basic 6 trig functions now, but does it make sense that just opens the door to utter insanity? In other words, I could say, okay, well, what about all the exponents now? Like what's the integral of sine squared? What's the integral of sine squared times tangent? What's the integral of tangent cubed times secant to the 4th? Like, so trig's involved now, but now you can just start messing with it. Does that make sense? And of course, we don't want to be that good at it. And we want to wade into that a little bit, but we don't want to be that good at it. So I want to finish with one other question. And that is this. Last. Let's try what seems like the simplest thing we could possibly choose if we want to complicate things with exponents, which might be the integral of, say, sine squared. Notice I didn't start with tangent squared, or I didn't start with cosecant squared. I wanted to start with one of the trig expressions that I know and like. And I didn't start with cubed or to the 4th or to the 5th or to the 18th or whatever. I started with like this next simplest thing I could think of. I didn't throw any other trig functions in there. I didn't say what's the integral of sine squared times cosecant or something like that, or cotangent or whatever. I didn't throw anything else in there. So I keep it really simple.
Could you do something really weird like integration by parts, u being sine of x and then du being sine of x dx?
Yeah. Do you find yourself, again, having some creativity to you? So again, let's just write down some options. So Vale is saying since sine squared is sine times sine, and that looks like a multiplication, then couldn't you potentially use integration by parts and let one be u and one be v prime and try that, which I'm very tempted to do because we haven't kind of used integration by parts yet in anything we've been doing. So I think we might go try that one. Anybody else have some other ideas?
could you replace it with a trig identity? Like, I know there's sine squared plus cosine squared equals 1. So could you do like cosine squared minus 1 or something?
That's exactly right. So sine squared is sine squared plus cosine squared equals 1. So that'd be 1 minus cosine squared. So notice that's a substitution, but it's not changing letters. You're still staying in x's. Notice that's kind of the same problem because now you're just doing it with cosine. Like the integral of 1 is no problem, right? We don't care about that. But now you have the integral of cosine squared, and that's kind of the same as the integral of sine squared. And so, yeah, absolutely, Eve. What else? I mean, couldn't you try, I don't know, u equals the sine of x? So now it's u squared. Like a substitution might go somewhere, right? And of course, from what I just showed you a minute ago, you could try something utterly ludicrous, like let's let u be cosine of x plus tangent. So it's like, oh boy, there's like 50,000 choices now. Let's try integration by parts just to see if it goes anywhere. So if I let u be the sine of x and v prime be the sine of x as well, since they're both the same thing, then u prime would be the cosine of x, the derivative. The integral of sine is cosine. I always get the negatives wrong. See, the derivative of cosine is negative sine. Okay, so that'd have a negative in front of it, right? Where'd my pen go? How come I can't write? I think my pen might have died. I'm going to put a negative in front of that as soon as my pen wakes up. So let's see, integration by parts. Again, I just taught that to you the other day, but I can't remember it, so I'm going to make it for myself really quick. So let's see, integration by parts. It was like u, if you have the derivative of two things, that'd be power product rule, u prime v plus uv prime. If I integrate both sides, then the integral of uv prime with the integral would go away, and then I just have the integral of the other two. And so I could say that the integral of uv prime, if I algebraically solve for that one, would be equal to uv minus the integral of u prime v. There we go, made it for myself. Again, don't make it for yourself, just look it up. You got it in your note sheet as far as the test is concerned, but it's just kind of cool to be able to make stuff for yourself, right? Just like I made tangent squared plus 1 equals secant squared. Okay, so let's see then, what does my original problem become? So that means the integral of the sine squared of x, which I'm sitting there thinking I can't do, would be equal to the uv, that's sine times negative cosine, so negative sine of x cosine of x. That's ugly, but I don't have to take its integral. Minus, and now I'm hoping this integral is easier. That's the key to integration by parts. Is this new integral easier than it was before? U prime, which is cosine of x, times v, which is also cosine of x. And it's negative, so that turns that into a plus. That's disappointing. Because it looks kind of like what it looked like before. Do you agree with that? In other words, hey, I was trying to find the integral of sine squared, and now I just traded it in for the integral of cosine squared. So
we could do it again.
Yeah, and that isn't a terrible idea. Like maybe that remember when I showed you e to the x sine of x and how we did 2 laps of it and suddenly we got out of the woods and I was like, oh my God, that actually worked. Now I'm suddenly having, and again, I actually did not plan to do this, but I'm suddenly having a really interesting idea here based on what one of, I think it was Eve that just said a second ago. Isn't this, remember, I don't really care about sine of x, cosine of x, because I don't have to take its integral, but isn't cosine squared equal to 1 minus sine squared? Why would that be cool to replace this?
Because now we have something else to do integration by parts with.
Even better. Even better than that. Why am I much happier to see another integration, another sine squared?
Because you could factor out that 1 and then the negative, I think, and solve for that integral.
Remember, because of the minus sign, I can do those two separately, right? That's the integral of 1 and the integral of sine squared. But algebraically, what can I do with this?
You add it to the other side.
Can't I add it to the other side like we did with e to the x and sine of x? Which means if I add it over to the other side, wouldn't I have 2 of them? And the integral of 1 with respect to x, isn't it?
That is crazy.
And so I'm going to rewrite. I don't like minus signs in the front, so now, honestly, I did not think that was going to work. I have a shortcut, cool method I was going to show you, and I thought that was going to be a dead end. But that seems to have worked. Now, does anybody have their trig sheet up? Is that actually the answer? Honestly, I'm pretty sure it's not. I'm going to see if I have it. I think I stuck it in here. Yes. I'm firing on all cylinders today.
The answer is just tangent of x.
What? So I'm looking for it. Notice there's titles, basic forms, integrals with roots, rational functions. Is there something that's titled like trig functions? There's exponentials, logarithms, trig. Bam. 61. There's the answer. X over 2 minus 1/4 sine of 2x. That doesn't look like what we got, or does it?
Well, we did get x over 2x minus something, so maybe we could manipulate the something to look like 1/4 sine 2x.
Yeah, in other words, maybe we could do some algebra. Remember with trig, you're never really stuck. You can always like change stuff out. You can switch out sine for cosine and tangent squared and all that stuff. Again, I have a chill running down my spine of glory, just thinking, my goodness, I can't believe that actually worked. I totally expected that to be a dead end. But let's see, let's think about this for a second. Anybody remember, have a vague recollection of an identity that had sine times cosine in it?
The one with the double angles.
That's exactly right. These are the sine of 2x is equal to 2 times the sine of x times the cosine of x. I've been teaching trig at night the last couple of days, and so these things are actually in my head now. And don't we have that? Well, we kind of have that, except for there's no 2 in front of it, right? So let's think about this a minute. Well, they're both divided by 2, so I guess I have x over 2, and then I have minus the sine of x cosine of x over 2. Is there any way to get a 2 in front of that sine of x cosine of x?
Well, that's where the 1/4 comes in, because then you can divide it by 2, and then if you multiply the 2's on the bottom, it becomes 4.
Bam. In other words, couldn't I multiply the top of this fraction by 2 and the bottom by 2? And so then doesn't that become x over 2 minus on top the sine of 2x over 4? Hey, it's the same thing they got. Now, I like mine better. I like mine better. The reason I like mine better is because the angles are the same size. Do you understand what I mean by that? In this answer, the angle's double the size it was before. I mean, I don't know if I like that. However, I understand why the book wrote it that way, or why somebody wrote it that way, just because it's a little tighter, it's a little more compact. That's amazing.
If you're just using the formula and not thinking about it, then I think the book one makes sense. But if you're working it out, they're kind of like ours. If you're
Yeah.
just plugging and chugging, you know, simplest is best. But yeah.
Well, and I would say if you're, like you say, plugging and chugging, if I said, what's the integral from 3 to 1? Like, you know, what's so hard about throwing 3 in there? Now it's sine of 2 times 3. Like, it's not that big a deal. There's less places. Generally speaking, what makes something simplified is, would you agree, there's 3 places to put x over here. There's 3 places to put 3, whereas here there's only 2. So that's a good argument for the answer that you have in your sheet being better, I think. Unbelievable. Good old number 61. Let me show you. I don't think I'm going to be 3 for 3. Do I have an identity sheet in here that I can bring up? I do. Man, on it today. Here's a pretty cool identity. See that guy? That's what I was expecting to show you. I was expecting what I just tried to not work. I was expecting it to lead to a dead end. Do you notice that gets rid of the square? In other words, if we're trying to find the integral of sine squared, and then it's like, oh, well, just find the integral of this other thing that isn't squared. That's a substitution, but notice it isn't changing letters. This is going to be easier, better, arguably. Let's try that. So I'm going to say easier with a question mark. Since the sine squared of x is equal to 1 minus the cosine of 2x over 2. Fortunately, I have to go back and see if that's true. It is. Then I could say that my easy integral would be the integral of 1/2 minus 1/2 cosine of 2x. Again, do you agree that's a substitution? It's taking one expression and changing it in for something else, except that I just didn't have to change letters this time. And notice integration by parts, we didn't have to change letters either. And I can do this. It's totally easy. The integral of 1/2 with respect to x is 1/2 x. The integral of cosine of junk is sine of junk, right? Because the derivative of sine is cosine. So there's a 1/2 here. The integral of cosine is sine. The junk stays the same. But the derivative of sine of junk is sine of junk times the derivative of the junk. So the fact that the derivative of 2x is 2 means I also have to come out here and divide by 2. Again, I should go slow and substitute. In other words, let u be equal to the sine of 2x, but we're kind of out of time. And notice that produces the same answer. So I think it really was easier. That was really fast. I didn't have to remember integration by parts. That was a pretty good substitution. So and again, I'm being lazy. I should say plus C there. Maybe I'll actually do it this time. I will tell you this and then let you out of here. This is what I was planning to do. This was my plan. I had actually prepared that. I'd played with that. And just to, I've offered you extra credits to try to run down those rabbit trails. But when I tried this plan, I made a substitution into U and I couldn't solve it. So then I made a substitution into W and I couldn't solve it. And then I made a substitution into V and I couldn't solve it. So I was like successful getting it from X to U to W to V. Like I made 3 different problems and I couldn't solve any of them. So I don't know if that's a dead end, but it was a lot of substitutions. Just I'll erase this, but the last one I got was the square root of V over 2 V plus 1 squared dV. Do you agree you're not out of the woods there yet? You can't just do that. You're going to have to go on and let G be V plus 1 or something like that. That was my 4th step. I was like, oh my gosh. So I don't know. Is it going to work? So it's amazing what could work. I guess that's what it comes down to. So we tried integration by parts and oh my gosh, it actually worked. Unbelievable. And to repeat myself one last time, this is hard. So as soon as we figure one of these things out, we want to make a trig table, right? We want to write this stuff down. And so you should kind of let's just stare at these kind of going out the door really quick. Notice like sine cubed, that's interesting. Notice that's kind of a surprising looking answer. We already knew the inverse of the integral of cosine was sine. That's kind of easy. Not surprised, if you will, that since we just found the sine squared, I'm not surprised that it's so similar to the cosine squared. Notice the only difference is a plus sign. Isn't that kind of weird that it's that close? The integral of sine times cosine. Does that make sense? That's a problem we could propose. I wonder what the integral of 2 trig functions multiplied together are. That's kind of interesting. I have a feeling that got replaced with 1/2 sine of 2x. Wouldn't that be an easy integral to take? You replace those two based on the identity we talked about earlier. We said 2 times the sine of x cosine of x was equal to the sine of 2x. So if I divided 2 by both sides, like that would be an easy integral. So that's not hard, I'm guessing. Let's see what other craziness is in here. Oh, trig's not done. Wow, look at that. The integral of x squared sine of x, like let's mix parabolas and sine together. This is what mathematicians do, right? Like they just go nuts. I wonder if there'll be something like the natural log of x times the sine of x. I wonder if that's in here somewhere. My guess is it's not. But they do have e to the x sine of x. Remember we made that one ourselves the other day. I made this one for you. That was that weird 2-step process that we just used again. That's kind of cool. Right, 3. If 2 is good, why not 3? X times e to the x times sine of x. Like how crazy can you get? And then there's cosecant. Notice there's even cosecant to any power, like cosecant to the n power times cotangent. So it's interesting because it sort of has the feel like, gosh, it almost feels like there's always an answer. But again, there's lots of things I don't see. Like here's some logarithms, but I don't see what's the integral of natural log of sine of x. Is that because there's no end to how big the table would get? Or is that because it was impossible? Like that's kind of fun to think about. We made this one for ourselves just the other day. Like we're starting into it. That's kind of cool.
There's a couple more logarithms, but not much.
Yeah, there's a couple more logs. Notice how huge they are. Like sometimes they're just terrifyingly gigantic. I like that they were lazy too. Notice they didn't put a plus C on the end of that. I like that. Notice there's some really crazy things like a minus x. Anyway, I need to shut up. So tomorrow we can still talk about 8.3 a little bit, and then we'll start talking about 8.4. And 8.4, just to preempt it, since we happen to be sitting in here, is this. Statements like this, where there's something that looks like Pythagorean theorem in it, like a squared plus x squared. Would you agree that looks like, hey, that's a Pythagorean theorem. That's a right triangle. If that's a right triangle, then if you get trig involved, that turns out to be a brilliant but somewhat predictable substitution. That's what 8.4 is about. So in some respects, we're going to spend 3 days on what I've kind of introduced today, which is good because we need some soak time. We could spend 3 weeks on this. All right, get yourselves out of here. I will see you tomorrow.
Are we going to have a final and a chapter 8 test?
Let me look at the syllabus because I don't remember that plan. Yes is the answer to that. And I'll review that very carefully because I could make that test in such a way that not one of you passed it, which I certainly don't want to do because it's like this a lot. We've talked about a lot of things. We still have a couple weeks left.
You have office hours at 12 today?
Yes, send me I don't go in there unless somebody texts me, just because most of the times people aren't doing it. So do you want to meet in there? That's absolutely good.
Okay, I'll text. Yeah, I'm having a hard time with the integration by parts.
Yeah, and that's not an easy one. What time did I say? And actually, I don't really care about the time because I'm just going to be working on other things. Does that time work good for you? Did I say 12? Is that what my syllabus said? Was it 12 or 12:30? It must have been 12:30 because I have a class on Tuesdays. So yeah, I'll go in my office at 12:30 today. I'm making a note.
I'll just I'll shoot you a text because I have another doctor's appointment today too. So
Okay. Yeah, shoot me a text if you want to adjust that time a little bit, or if it doesn't work, just send me a text. I'll wait to hear from you and then I'll go in there.
Yeah. Don't have anything going on this morning until my appointment later this afternoon.
Okay. Well, we can certainly talk right now too if you want to. At least
If you want to, that's fine with me.
yeah, I'm okay with that. I'm always willing to stay after class. So
Okay. I was just going into the homework that's due this Sunday. And lurking on like the 8.3, but I'm not really getting how to set up the integration by parts.
yeah, so let's take a look at that.
Real quick before you start,
Yep. Go.
last week I sent you a couple emails and I haven't heard back yet, so I'm not sure if you found them or not because things can get lost in email.
Yeah, I didn't look at your email a ton this week. I did see one from you that had extra credit in it. And that's,
Yeah, and I sent another one. So anyway, if you could get to that,
yeah,
I don't know, whatever works for you. Just letting you know.
yeah, that's my plan after this, is to get on email. So I'll probably get back to you in the next couple hours.
Have a great day.
You too. So the key concept behind integration by parts is if you stare at this and say, that's hard. The question is, if you change it to this, I won't say is it easy, but is it easier? Notice the only difference is this had a one term and another term, and this is basically saying, well, what if you took the derivative of this term and put it there, and you took the integral of this term and put it there? Would that answer be better? And it's based, and that was made from product rule. And so, and it kind of makes sense. So the backbone of it for, say, a problem like this, say I was sitting here with x times, let's see. Let's try x times the tangent of x. So you look to integration by parts when you see junk times junk, when you see two things multiplied, because it's kind of the alter ego. Integration by parts is the alter ego of the product rule. So there's no way I'm going to put that together. And so I'm staring at that thinking, I can't do that. I don't know what to do. I know the integral of tangent now, thanks to today. And I know the integral of x, but it's not as simple. It's not, there's not a plus sign between them, so I can't do them separately. And so it's much more complicated. So the question is, if I assigned one of those to be one and one the other, and the simple approach to, or this is a classic case of a situation that's definitely going to help. And the key is really this right here. In other words, what was u, you get to take its derivative. So does it make sense if I chose this to be u? The derivative of x is actually 1, and so that's effectively going to make that go away. So I don't like multiplications. That's the problem. And this is going to make that go away. So if I pick that to be u, then I'm forced to pick this to be v prime. And so, okay, let's make a list then. I've got u is x, so that means u prime is equal to 1. That's very helpful. And I chose v prime to be the tangent of x, and we found out today that the integral of the tangent of x, if I remember right, was negative natural log of the cosine of x. So ooh, that's maybe this isn't going to be so good. So again, the concept has to, all of these have to do with, I'm staring at one integral that I can't take. And so if I make a substitution, do I create a new integral that I can? Or if I use integration by parts, did I just create an integral that I can take? So let's find out. So I had the integral of x times the tangent of x. And now I'm saying u times v. I don't have to take the integral of that. That'd be x times that. So that's very terrifyingly ugly. But I don't care because I don't have to take the integral of it. So there's u times v minus the integral of u prime, which is 1, times v, which is negative natural log of the cosine of x. And it's negative. So a negative times a negative is a positive. So I really just end up with the natural log of the cosine of x. Oops. So the question is this easier? Can I do it now? And I sort of feel like, no, like that's not very easy yet. Does that mean I blew it? Because I just made this problem up. No, it just means it's not simple. Not simple. I guess my next move would be to try to try to let u be cosine of x or something like that. But that's how you set it up, Alicia. Does that make sense?
Yeah.
Kind of very
I,
important to kind of write this down over here.
and seeing like it's not the easiest to see if it's going to end up being any better or not.
Yeah, and that's kind of why I did what I did today, because I wanted you to feel that tension, because teachers will make it look like, oh, it's obvious you do this and you do this. Yeah, if they're canned book problems, it's obvious. But if you just make stuff up, and especially like in your case, you're just learning this, you don't have any instincts yet on, things that you don't kind of know ahead of time. Oh yeah, that's not going to go anywhere. You have no experience in it. So that's why I'm saying, I think it's very important to stop right here and say, bam, success. I succeeded in getting a new problem for myself. Now, I might look at it and go, well, that's not total success because I still can't do it. But I'm not daunted. Like, I can now try something else. And again, I made this up, and so I'm really curious. Like, is there an answer to x times the tangent of x? Is that one of the ones that's sitting in that table? Like, if I went back and looked at it. So I only have two tools, substitution and integration by parts. And so now that I tried that, and it felt like I needed to do that, just because I noticed those aren't two trig expressions, like tangent times x. I mean, I could switch out tangent for sine over cosine, but now I got three things. This feels really daunting. If I was to continue, which because of your question, I'm not going to, but my next move, I think, would be to try. I never liked junk inside of junk. In other words, I could handle the integral of the natural log of x. So then why not let u be equal to the cosine of x? So that becomes the integral of the natural log of u. The question is that going to, just like this problem did, create something else ugly that I can't get rid of? And the answer to that's probably yes. It's probably going to be still not doable. That's my instinct. It's still not going to work. And so maybe this is impossible. Maybe we got to come up with some substitution that's ludicrous from nowhere, like secant substitution was. And so
okay, I'll when you post the video today's, I'll go back and look and watch it. I sent you an email. Yep. I missed the majority of the class because I was at the hospital. Yeah,
I got your email. I just didn't have time to respond. I saw it this morning because I quickly looked before class, and I appreciate when you let me know that, because I do like to know. And the video from today was really important, because we just saw how complicated this process is and how interesting and surprising, actually, frankly, when what we try actually works. Should think more like it'll never work. And when it does, like, oh my God, I can't believe it.
Well, thank you for showing me that. That definitely helped a little bit.
Yeah, sure. Other questions?
I had a question about that last problem on the 8.1 homework, if no one else has a quick question.
You're always very polite and patient and wait too long, so jump in, Cheyenne.
So I actually cheated to get the point on that homework, and I looked at what the website was doing, and I kind of picked up from there, and I was wondering if you could look over my scratch paper, because the answer that I was getting wasn't the same as the correct given answer.
Yeah, so tell me what your problem was that you solved, so I can kind of play with it a little bit. Well,
it was e to the 21x.
Oh yeah, that one.
Yeah, 1 plus e to the 7x.
21x. 21 and 7. Okay, go ahead.
Yeah, so I actually took a picture of my process, and I'm just going to share my screen.
Yep.
Okay. So this is what I started with, and then I got stuck here, and I plugged it into one of those solvers, and this is what I saw them using, so I kind of worked out from there. But my answer is slightly different from the correct answer.
Got it.
Which I can pull up.
Blow that up a little bit.
Oh.
That's good. So you said u equals that. So dx. X 7e to the 7x. Yeah, that's right. So then you threw that in there. You had that. E to the 7x. Yeah, you subtract exponents, so that'd be that. U minus 1 squared. Squared, yeah, that's right. Okay, go down. So yeah, at that point you're home free, because when you have u minus 1 squared over u, the fact that that multiplies out and then they all divide by u gives you a bunch of separate problems. So yeah, that's awesome. So that idea didn't occur to you, right? That's what you're saying? You had to kind of cheat to get that idea?
Yeah, this part was, this was new to me when I plugged it into the solver, because I think I got stuck over here. So this was what I got.
Yep.
And then
yeah, and then you thought, oh, I'm stuck. And from today's lecture, you probably would have thought, oh, I'll let w be u minus 1 or u minus 1 squared. But whenever there's not a plus sign on the bottom, this was kind of the very first integrals we ever took. And it was so long ago that probably that idea didn't occur to you. But because you have a bunch of junk on top of it, but it's just divided by u, because of distributive law, they're all divided by u. So multiplying that all out and creating a bunch of plus and minus signs, we love plus and minus signs with integrals. And so, yeah, that's an example of what makes this material so darn hard, because it'd be easy to kind of run down the wrong road. In other words, you were almost there. All you had to do is like take a right turn and you were at the store, and you took a left and now you're like way out in the country and lost again and so forth. But you just got to accept that's kind of part of this. So now you look at it and go, okay, that makes sense. Awesome. Let's see. I don't see anything wrong with any of the stuff you just said.
yeah, so this is what I finally ended up with, which once I typed that in, the website marked it as wrong, and their answer had, I think, like a 14 or something down here. And it
Yeah,
looked a
so
little different.
look, you made one dumb mistake. Look at the very top of yours. See where it says the integral of u? What's the integral of u? It's not just u squared.
It's u squared over 2.
U squared over 2.
Okay. Yeah, that's what it was. Okay. Yeah, that explains it, because I was, yeah.
Yeah, it can be really hard to find stuff like that when you're looking at like a page of work that you just did.
Yeah, sometimes you just need a second pair of eyes.
That's exactly right, because you could stare at this forever and never see it. I mean, that's an example. Like if you had done that on a test, I would have probably given you full points for it. I would have just pointed at that and said, dude, and you would have thought, dude, when you looked at it. But it's like you did so much good stuff there. But that's what worries me about this next test, because I mean, I'm certainly not going to give a problem like that on the next test.
Yeah, that was my next question. Like, should I run through this a bunch of times to make sure that I'm doing it right?
No, the main thing is just to, take seriously every question. Just because you gain intuition, every problem that you do, you gain intuition. And so as long as I, ramp it way back and give you easier problems kind of from the, stuff that was kind of main and plain, if you will, then you'll be fine. But it would not be weird at all. I mean, I would sort of expect every person to have one problem on the test where they just kind of do the wrong thing. I mean, it's kind of like you were doing there. It's like you had u minus 1 squared over u. It was like you're home free. but you don't see that. And so then you replace U minus 1 with W, which is going to put a plus sign on the bottom, which is going to totally screw it up. And then, you know, there goes 15, 20 minutes. And then you start doubting yourself and like your whole test is wrong. And that's kind of an easy thing to do. In some respects, like the people that are like you and Justin, actually all four of you, if you're still there, the sharper people are going to tend to make stuff a little too hard. Like you feel confident going way out in the weeds, if you will. And so, you know, interesting. Good job.
That velocity problem kind of threw me for a loop, because when I was first reading it, I was like, well, wouldn't that just be the integral of it? And I was like, then I really looked at what it was, and it was like, oh, it's not all going to be zeros. When it's at 0, there's a 1 tucked in there with the
Yeah.
heat or whatever.
Yeah. I know.
Yeah, I figured it out, but it was like, oh, okay.
Yeah. Well, I credit, in my case, my depth of understanding of math has to do with gazillion hours in the weeds, frankly, just not giving up and staring at stuff, because I'm not naturally good at this stuff. I've told you that it's something I have to kind of work at, but I get bothered by something that doesn't kind of work quite right, and I'll stare at it forever. And many times it's because of something small and stupid. And the more I, you know, waste a half an hour staring at it, I tend to make those mistakes less and less as time goes on. But that's good for you, I guess, is what I'm saying, even though it's super not fun. Keep going. What else?
Okay. Yeah, I think that was my only question.
Awesome.
Have a good day, guys. I'm out of here.
All right.
See you tomorrow.
See you tomorrow.